Hello, in this video, I would like to talk about linear algebra, especially matrix operations. This tutorial is a preparation for our discussion on the PCA, primary component analysis. Okay. For this tutorial, we will not use a NumPy matrix class because it is no longer recommended to use this class even for the linear algebra according to their official document. So instead, I use a regular arrays. So that's what we're going to do. And this matrix, NumPy matrix class may be removed in the future. For more details, go to this document and they will talk about it. Okay. All right, let's create arrays. We're going to create arrays as matrices anyway, as we talked about over here. Okay. All right, so let's import a NumPy first, as usual. Okay, when you create an array, you can use a tuples like this, parentheses, tuples, or you can use a list, as you can see over here. So either way is fine. Also, you can specify the type like this. Okay. All right, although you don't have to. Okay. So in this case, I just want to make sure we are going to use a float. So we have a 1, 2, 3, and then a 3, 4, 2. Okay. And then assign it to let's say A. Okay. Look at it. Then we have a array or a matrix of 2 rows and 3 columns. Okay. You can take a look. So array is an array of a float 1, 2, 3, 3, 4, 2. Okay. And we can check it. So it's an ND array. Okay, n dimension array. How about the shape? 2 by 3, so 2 rows and 3 columns. How about how many dimensions? ND, number of dimensions. So we have 2 dimensions. Okay, 1 and 2, 1 and 2. Okay, if you print it, so 1, 2, 3, 3, 4, 2. Okay, so we have a 2-dimensional array like this. Okay, so we're going to use this as a matrix. Okay, well this time we're going to create an array using list. Okay, so both are tuples and list of both are sequences. So both are working. So we want to have 5, 6, 7, 8, 34. Okay, so looking like this. So since we didn't specify the data type, this time they use the integer 32 because we type these numbers as integer instead of a 5 point or 6 point, and then it's gonna be the float. Let me show you. So if you make it like a 5 dot, okay, and then can you see that array of floats? Okay, if you don't, it's gonna be integer. Okay, anyhow, so let's do that and let's take a look. So 5, 6, 7, 8, 3, 4. So and then we can check the type and the array. Okay, and the shape 3, 2. Okay, let me show you again. So here we have 3 rows and 2 columns. Okay, 3, 2. Okay, dimensions 2 dimensions. We have the rows and columns. Okay. So 2 dimensions. Can print it. So 5, 6, 7, 8, 3, 4. Okay. So not too bad. Actually, we already talked about this a long time ago when we discussed the basics of NumPy. Okay. How about using a range? Okay. So how about over here you have to type all these numbers. That's not nice. So how about all the numbers starting from 0 to 8? Okay, 9 numbers. Okay, So if you run this part, here we have 0, 1, 2 all the way to 8. Remember, 9 is not included. Okay, and then we reshape it 3 by 3. Okay, so can we reshape this one? So now 3 rows and 3 columns. Can you see that shape? Okay. How about we create array starting from 1 to 9. Okay, and then I reshape it 3 by 3, and then assign it to C. Okay, so 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay. All right, let's create an array of all zeros. Okay. So we have 5 zeros. 1, 2, 3, 4, 5. Okay. Or we can have a matrix like 2 rows and 3 columns, like this. 2 rows, 3 columns. Or we can have a square matrix. When the number of rows and columns are the same, it's called a square matrix. If m is equal to n, it is a square matrix. Okay, like this, all zeros. Okay. How about all ones? Array of all ones. Excuse me. So 1, 1, 1, 1. Okay. Also, you can have a matrix, 2 rows and 3 columns. Okay. All ones. How about square matrix? Over ones, 3, 3. Okay, 3 rows, 3 columns. Okay. Also, you can specify the type if you want to. Well, it doesn't matter. But like this. Okay. Over here, these are floats. Can you see the difference? So 1 point something, 1 dot. Over here, just 1. So there's a difference. Okay. How about diagonal matrix? Diagonal matrix is a matrix only the non-zero entries are located on the principal diagonal. Okay, and everything else is zeros. Okay. Okay, let's create an array of 1 through 9. Okay, 1 through 9, and then we reshape it with the 3 rows and 3 columns and assign it to C. Okay. Now like this, 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, and then let's take a diagonal. Okay. So numbers on the diagonal over here is 1, 5, 9. Do you see that? 1, 5, and 9. Okay. Okay. Actually, you can get the same thing using this way. See that diagonal. Okay. Same thing. Or another way is np.diag. So you can get the same numbers on the diagonal many different ways. Alright, so now are we ready to create a diagonal matrix? Okay, np.diag. Okay, then can you see that np.diag C? Okay, this one gets the numbers on this diagonal. Okay, it shows you over here. Right. So what this one does is they create a diagonal matrix using these numbers on the diagonal. Alright. So 1, 5, 9, and every other elements are zeros. Okay, it's a diagonal matrix. Alright, let's look at the identity matrix. This is a special type of a diagonal matrix. Okay. The identity array or matrix is a square array or matrix with the ones on the main diagonal. Okay, so let's do that. Okay, so np.identity 3. Okay, this will make a 3 by 3 identity matrix. As said over here, on the diagonal is all ones, and everywhere else is all zeros. Okay. The identity matrix actually has a very interesting property. Let me show you. Okay, so let's say we have a matrix A, which we defined up there. Okay, So A is a 2 by 3 matrix. Okay. When you multiply A by this identity matrix, let's see how it goes. So exactly the same. Okay. You can think identity matrix more like a 1. So when you multiply any number by 1, well, it's going to be the same number, right? So same kind of idea. Okay. But if you multiply II by the matrix A, you're going to have an error like that. Okay. So why don't you wait for the multiplication part below, and then come back and say what's the problem. You need to think about it, and then I think it's going to be obvious. Okay, so let's look at C. So C is a square matrix, 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, so when you multiply C by II, guess what? Exactly the same thing. Okay, when you multiply II by C, guess what? The same thing. Okay, so identity matrix is actually used a lot in the linear algebra. All right. Okay, let's look at a transpose. We use a transpose a lot actually in machine learning project. Okay, so what this does is we replace Aij by Ji. Saying the same thing differently would be you just basically change the columns and the rows. Okay, so let me show you some examples, and then it will be obvious. Okay, so here we have a 2 by 3 matrix. Okay, let's look at the shape 2 by 3, 2 by 3, and then to transpose we use this operation T, A dot T, this method. Okay. And then once you transpose it, let's put it on a T, okay? All right, that's it. Pretty simple, huh? So let me show you T over here. So like this. All right, so let me show you. Initially, we had A. Okay, so this is A, 2 by 3. Okay, and then once we transpose A and assign to T, it's going to look like this. So simply speaking, the row over here, 1, 2, 3, becomes a column. Make sense? And the second row, okay, becomes a second column, 3, 4, 2, 3, 4, 2. Okay? Or you can say, first column becomes a first row. The second column becomes a second row. The third column becomes a third row. Okay, make sense? Okay, so let's look at the shape. So it's now 3 by 2, from 2 by 3 to 3 by 2. Okay, okay, like this. So again, 1, 2, 3, 3, 4, 2. So, and then first row becomes a first column. The second row becomes a second column. Okay. All right. One of the term you may want to know is this concept of a symmetric matrix. So if A dot T, transpose of A is the same as A, we call it a symmetric matrix. Okay. So let's create a matrix, zero matrix S. Okay, so it's all zeros. And if you transpose this one, same thing. So obviously S is a symmetric. Somehow, if you don't like this method, T, you can use a little more wordy one, like a transpose. Okay, so same thing. Like this. Okay, but why you want to type this long word, T seems to be just fine to me. Okay. All right, let's look at a matrix addition. Okay, so let's create two matrices, P and Q. Okay. and Q. So if you look at P, so here we have a 3 by 4 matrix, and then a Q, also 3 by 4 matrix. Okay, so if you add a P with a Q, okay, so P plus Q is basically element addition, element-wise addition. 0 plus 10, 10, 1 plus 11, 12, 2 plus 12, 14, 3 plus 13, 16, and so on. So 8 plus 18, 26, 9 plus 19, 28, and so on, okay? So basically add these elements one by one, all right? P minus Q, same thing. So basically all minus 10s, okay? All right. Let's look at a scalar multiplication. So this one is multiplying a matrix by a scalar, okay, by a number. All right, so let's say A is a matrix like this, 1, 2, 3, 3, 4, 2, and you multiply that by 3. So basically, you do a element-wise multiplication, okay? So 3 times 1, 3, 3 times 2, 6, 3 times 3, 9, and so on. 3 times 3, 9, 3 times 4, 12, and 3 times 2 is 6. Okay, let's look at the shape. Let's look at if you actually multiply A by 3, same thing. Okay, exactly the same thing. Okay. If you don't like this notation, you can use a wordy one like this. Exactly the same thing. Okay. So np dot multiply 3 comma A, exactly same as this. So somehow if you like this one, you can use that. So it's up to you. Same thing. This one, the same thing. Okay. All right. Okay, let's look at a matrix multiplication. Okay. To multiply two matrices like A times B, okay, you have to make sure the column of the first matrix must be the same as number of rows of next second the matrix. So A is n by k, and B is k by n. Okay, this one can be you can multiply these two matrices because they are the same, and then the resulting matrix will be m by n. Okay. In terms of operations, according to this numpy.org official document, numpy dot is not preferable. Okay, you can use numpy dot, but according to this document, if both A and B are 2D arrays, that's matrix, it is a matrix multiplication. Okay, but using madmul, okay, or A assign B is preferred. Okay, so we'll use this one most of times. If somehow like a wordier option, you can do that too. But to me, just typing one keystroke would be to me it's better. But it's up to you. Okay. All right. So let's say A, so 2 by 3. B is 3 by 2. Okay. So let's take a look. Okay. So 2 by 3, 3 by 2. Okay. Can you see that? MK, KN. So this one, the same. Okay. So you can multiply the A and B. Okay. All right. So if you do that, it's can you see that 2 by 3 times 3 by 2? So it's gonna be 2 by 2. Okay. Looking like this. Or another option is you can use this function madmul, like a matrix multiplication. Same thing. So it's up to you. You can use this one or you can use this one. Okay. How about this one? B multiply B A like this. Okay. So B is what? 3 by 2. A is a 2 by 3. So still, we can multiply these two matrices, but the resulting one would be a 3 by 3. Okay. All right. So let's look at C. Okay, C is 3 by 3, 3 by 3. Okay. So remember, A is a 2 by 3. So A multiply by C. Okay. It should work. 2 by 3 times 3 by 3. So resulting one would be 2 by 3. Okay. How about this? B times C. Obviously error. Why? Because the B is what? 3 by 2. Okay. 3 by 2. Can you see that? And the C is 3 by 3. So B times the C doesn't work. Okay. But C times B should work, right? So C times B. That one should work. Okay. So if you go back to our previous example, okay, over here, now you understand why this one does not work. Okay. For example, A by II, it should work. Okay, but II times A, this one doesn't work. II is a 3 by 3, A is a 2 by 3. So over here, 2, 3. So obviously this will generate an error. Okay. All right, let's look at a different type of multiplication, element-wise multiplication. All right, let's look at A, okay, and B, same thing. But actually, to do a element-wise multiplication, we have to have a same shape. Let me show you. A times B, this will make an error. Okay, doesn't work. So we need to make a B, the second one, as the same shape as the first one. Okay, so let's do a transpose B. So B transpose and assign it to BT. Okay, so here we have a BT 2 by 3, A 2 by 3. Okay, so A is 1, 2, 3, 3, 4, 2. BT is let me show you. BT is a 5, 7, 3, 6, 8, 4. Okay. Okay, and then BT. Okay, so A times BT. This time notation is a asterisk. Okay, the star. Okay, so A star BT. That's a 549. That's kind of different from the one above, right? So this time we actually multiply element-wise. So 1 times 5. Okay, that's 5. 2 times 7, 14. 3 times 3, 9. 3 times 6, 18. 4 times 8, 32. 2 times 4 is 8. Make sense? Alright, so be careful. The notation very different. Over here we use the S sign. Element-wise multiplication, we use a asterisk. Okay. Alright, so we already showed it. A times B like this. That does not work because we cannot go by elements. Okay. Or if you somehow do not like this the asterisk, you can choose a wordier one as usual. So multiply A comma BT. Same thing. Okay. So if you like this option, you can use that. If you like this option, you can do it too. So either way, whichever you like. Alright. Alright, let's look at how to calculate determinant. Obviously, determinant is a very important concept in linear algebra. There are many good books and documents available, so you may want to take a look at what it is. Okay, over here, we'll just show you how to do that using the NumPy. Okay, so the syntax is NumPy dot linalg, linear algebra, and the det, like determinant, det. Okay, so let's do that. Okay, so this will generate an error and read the message y. Okay, over here, the 2 dimensions of the array must be square. So you have to have a square matrix, right? So meaning number of columns and the rows must be the same. Okay, so all right, no problem. So let's create a square matrix like this. Okay, 2, 6, 2 by 2. 2, 6, 4, 3, okay, and then assign it to a v. So let's look at v. All right. So v is 2, 6, 4, 3. If you look at the shape, obviously 2 by 2. Okay. So now we can calculate determinant. Okay. So numpy dot np dot linalg, linear algebra dot det, determinant, and then a v. Okay. All right. So minus 17.999999, whatever. Okay. Getting a determinant value is required to calculate a inverse of a matrix. So let me show you how to do a matrix inversion now. Okay. Well, syntax for inversion is extremely simple. INV, like inverse. Okay. By the way, to save some typing, let's import INV from numpy.linalg, okay, linear algebra. Otherwise, we have to type the whole thing all the time, and that's no fun. Okay, so let me import INV so that we can directly use INV without typing np.linalg.inv or something like that. Okay. All right, let's get an inverse of A. Obviously, this will generate an error. All right, so that have to be you have to use a square matrix. No problem. So just like over here, let's create a V. Okay, 2 by 2, 2 by 2 matrix. Obviously square. Okay. Get an inverse of V. All you need is inverse, inv B. Done, actually. So if you want to look at it, right there. Okay. Okay, inverse of this matrix will be itself, right? Okay, take a look. Inverse of V, that's the inverse of a V. And inverse of V, that should be the same as V. Is that right? Yeah. See, 2, 6, 4, 3. Okay. And also, if you multiply a matrix by the inverse of that matrix, guess what? You get a identity matrix. Sort of like the 3 times 1 over 3. That's 1. Okay, so that's it. All right. All right, let's look at the concepts of eigenvalues and eigenvectors. These two concepts are very fundamental to our discussion about PCA, primary component analysis. Okay. Okay, these two concepts are not necessarily easy to understand. So if you haven't taken any linear algebra class, it's not necessarily easy to understand these two. But anyhow, in this class, in this tutorial, basically I'll just show you how to get these values using NumPy. Okay. Simply speaking, let's go to this website. Simply speaking, we want to we want to find the eigenvectors like the V over here, okay, and the eigenvalues. Okay, so given some matrix A, we want to find the eigenvector. A times V is equal to gamma times V. Okay, and those gammas are eigenvalues. All right. Okay. All right. Let's take a look. And also, if you go to this website, there are some. There's an interesting definition over here. So let me read it anyway. In linear algebra, an eigenvector is a non-zero vector that changes by a scalar factor when the linear transformation is applied to it. Okay, the corresponding eigenvalue, often denoted as a gamma, okay, this is a gamma, Greek letter gamma, is the factor by which the eigenvector is scaled. Well, it doesn't make a whole lot of sense, I guess. So you may want to read some book or explanation in detail, but in this tutorial, I'll just show you how to get those numbers. All right. So let's create a the matrix. Okay, 3, 4, 2, 2, 6, 7, and so on. Okay, and then assign it to A. Okay, so let's look at A, how it looks like. So we have a 3 by 3, 3, 4, 2, 2, 6, 7, 3, 4, 1, 3 by 3 square matrix. Okay, to get eigenvalue and then eigenvectors, syntax itself is extremely simple. All you need is np dot linalg, okay, and then eig. That's it. Okay, that's it. Really. Okay, and then you're gonna have basically two things. Okay, the one at the top. These are the eigenvalues. These are the eigenvalues, and these are the eigenvectors. Okay. If you want to split eigenvectors and eigenvalues and put them in a separate variable, you can do that. Okay, so this one this will generate basically two things: eigenvalues and the matching eigenvectors. Okay, so you can return them to W and V. Okay. Okay. All right, so let's do that. Okay, so if you look at W, that's eigenvalues. See that eigenvalues, and then V, those are the eigenvectors. Okay, how about this way? Okay, so eigenvalue 11.25, matching eigenvector is the first column, 0.47, 0.76, 0.43. Second one over here, eigenvalue 0.505, and the matching eigenvector is a 0.75, 0.600, 0.25, and then negative 1.75 eigenvalue is matched by this column, 0.29, 0.68, 0.672, and so on. Okay. All right. So, well, some of you may find this kind of difficult to read. Okay, no problem. Then you can transpose it. That may be a little easier to see. Okay, then the first eigenvalue is matched by the first row. Okay, so instead of the first column, we can look at them as opposed to row. The same thing. The second row becomes a second. So the second column becomes a second row, and the third column becomes a third row. Okay. All right. So how about this one? you can do that too. You can see both of them together. So eigenvalue 11 point something, eigenvectors are these. It's probably this one. Okay. Or if you want to use a transpose one, you can use this way, the first row rather than first column. Same thing. All right. Or you can do the whole, two things together, and then you can use a for loop. Then you can have all three of them separate. Probably a lot easier to read, and this can be kind of confusing for most people. So if you present it this way, obviously looks better. Okay. All right. Let's check the our solution is actually correct. At the beginning, we said that we're going to find the eigenvectors and the eigenvalues given some matrix A. Okay, so let's do that. So let's multiply these values and see whether they are actually correct or not. Okay. All right. So first one, so AV, that's A original matrix we have. And the first eigenvector, okay. And then we have this vector, and then we can calculate the eigenvalue. That's the first one, okay. So eigenvalue times eigenvector, okay. See, they're exactly the same. So actually, our solution is absolutely correct. So you can do the same thing, but this time instead of using a original output, we transposed it, okay, v dot t, okay. So if you do that, so all these are exactly the same, okay. And then you do the same thing for the second eigenvalue, and the second eigenvector. So absolutely correct. Okay, can you see that? Exactly the same. And then next one. The same thing. Okay. All right. So the syntax again is pretty simple. This is it, but concept itself is not too easy. Okay. But anyhow, so once you know how to calculate these numbers, actually, there should be no problem understanding PCA. But we'll get into more about this when we discuss PCA, primary component analysis, later. All right.